Now we will look at the theory of the discrete time Fourier transform a little more carefully. Okay, so we define the original definition of the discrete time Fourier transform is x e of j omega is equal to summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay. So, this is the original expression. Now, if I want the discrete time Fourier transform to exist, that means the absolute value of x e of j omega must be less than infinity for all values of omega. Then I can say that it is finite and it exists everywhere. I will have to check only in the range minus pi to pi because this is a periodic signal and we can verify. So, this is the condition for the existence of the Fourier discrete time Fourier transform. Condition for the existence of the discrete time Fourier transform. So, what is this condition impose on that? So, if you look at the right hand side, it will be modulus of n equal to minus infinity to infinity x of n e power minus j omega n. This has to be less than infinity, and we know that the modulus of the sum is always upper bounded by the sum of the modulus of the terms. So, this is some less than or equal to n equal to minus infinity to infinity modulus of x of n e power minus j omega n modulus. This is the same as you split this into two terms, summation n equal to minus infinity to infinity modulus of x of n modulus of e power minus j omega n. This is equal to 1. So, I can drop it from the expression now, which says that if modulus sum equal to n equal to minus infinity to infinity modulus x of n is less than infinity, then this will guarantee that mod x e of j omega is less than infinity for all values of omega. Okay. So, this condition, what is it called? Remember, we had looked at this particular aspect when we were looking at the properties of sequences. This condition is called absolute summability. Absolute summability. Okay. Remember, we looked at it in the context of bibostability. Absolute summability is a very, very useful quantity, and it turns out that it was there useful in bibostability, but it's also the condition that is needed for the existence of the discrete time Fourier transform. So, if somebody were to ask you what is the condition for the existence of the discrete time Fourier transform, the answer would be that the input sequence must be absolutely summable. Okay. Another way of saying that of this statement is that all bounded sequences, all bounded and absolutely summable sequences, absolutely summable sequences for all of them, the discrete time Fourier transform exists, and the convergence of the discrete time Fourier transform, discrete time Fourier transform is an infinite summation, and the convergence of the result to the expression is a uniform convergence. Okay, uniform, there is no conditional, it's basically it converges uniformly towards the final result. Okay. Now, let us take a particular, a specific example. Okay, example. We have an infinitely long sequence x of n equal to a power n u of n. We said that the expression for the discrete time Fourier transform x e of j omega is equal to 1 over 1 minus a e power minus j omega. Okay, we wrote down this expression under certain assumptions. Now, what is the condition for the existence of the Fourier transform? The condition for the existence of the Fourier transform will be summation n equal to minus infinity to infinity mod x of n. We have to check this, and this will be equal to, in this case, summation n equal to 0 through infinity mod a of n. This will be equal to 1 over 1 minus mod a. This will be the convergence result if mod a is less than 1. Okay. So, the condition for the existence of this Fourier transform, condition for the existence of this Fourier transform. We did not have to actually compute it. We can say the condition even from by looking at this expression. A condition for existence of discrete time Fourier transform is mod a less than 1. Now, if you go back and look at when we derived this expression, we got a geometric series, summation n equal to 0 through infinity a power n e power minus j omega n. Okay, and this was what gave us the expression 1 minus a e power minus j omega. And if you remember, we said that this geometric series will converge if the absolute value is less than 1. A e power minus j omega is less than 1. This is the same as mod a less than 1. So, from the expression from the Fourier transform also we got the condition that mod a has to be less than 1. We can also apply it to the sequence itself and get a condition which says, okay, this is how. So, given a sequence, first thing to check, is it absolutely summable? If it is absolutely summable, then we can say that the discrete time Fourier transform exists and there will be uniform convergence when you compute the expression for the discrete time Fourier transform.